Hello, everybody. I'm going to go through the solutions of the question 33 for the course MATH1251 at University of New South Wales. This is for the calculus section of that course. In this question, we are going to solve a differential equations, ordinary differential equation, related to the logistic curve. Basically, this is a model for the population growth. A general model. There are other models, there are many other models, but this is the basic one. So this is a differential equation that we would like to solve. These little k and big k's are the sum constants. The first question is that we would like to find out the two constant, stationary solutions of this differential equation. Now that means, what is this? How we can find out stationary solutions? We let the dy dt is equal to 0, and as the derivative of the of a constant is 0, right? So constant solution means that y is a constant. If y is a constant, the derivation will be 0. So this is equal to 0. If this is equal to 0, then there are two options. Either this is equal to 0 or y is equal to 0. So, but we want to find out the y. That is this, because y is a function of t of the times. Phi is the process that we are dealing with. That y is the function representing the population growth. As I said, with this equal to 0, either this is equal to 0 or y is equal to 0. If this is equal to 0, gives us the y is equal to big K, or y is equal to 0. So these are the two constant solutions, constant stationary solution for this differential equation. It's pretty straightforward. And also stationary solution is called the equilibrium solution. Second part of this question asks us to find out the solutions for the ordinary differential equations. And given the particular solutions, y is equal to y0 at t is equal to 0. So from the beginning of the process, we have a constant y0. And assume that y0 is given. It doesn't matter with whatever it is, but it's just given. And otherwise, in other times, y0 range some number between 0, positive number between 0 and k, not 0 and not k. So k is the maximum of the possible values. So this is a separable differential equation. It means that we can write the integral with respect to y in one corner and with respect to 2 in another corner, left-hand side and the right-hand side. That's a separable ordinary differential equation. Then this part is y going through there, and let the k here act as dt. And this is the integral that we need to solve, k, right, for the big k's. So this is a partial fraction. We need to use a partial fraction to be able to solve this integral. This is simple, as we know. It's immediate k times t for the right-hand side. For the left-hand side, we need to calculate the partial fractions, as we've done last week. And this was the partial fraction for this, because the denominator is two linear factors. One of them is just y. That's y minus 0, y plus 0, whatever you like, and k minus 0. So you have two factors, so you need to find out the constant a and b satisfying this condition. So we need to multiply this fraction by k minus y. We need to multiply this by y because we want to make the denominator is equal to, so that we will find this is equal to that part. And when we do that, the coefficients of k will be 1, and the coefficient of y will be just 0. So this is what we are doing here, because in the left-hand side, and I'm omitting the denominator in that moment because it's all same when you multiply it. So k here, we have ak minus ay, ya. Here we have only by. We are not changing, we are not moving objects here. We are thinking this equality in terms of the equations, in terms of the polynomials. So only thing that you want to do for this part, I explained this last week, but let me explain again. So the equality, you're not getting this constant on the other side. You are making this as a polynomial with coefficient 0 for y, and this is the constant term. So you're making the coefficient of y is equal to the coefficient of y on the other side, and the coefficient of k is equal to coefficient of k here, which is 1. So you're thinking to make the two polynomials are equal if and only if their coefficients are equal. So that's the idea. Okay, from here we have a is equal to 1. Since this one minus a plus b is equal to 0, we have a is equal to b, a is equal to 1, b has to be 1. So this will be 1 over y and 1 over k minus y. So this integral can be written as this integral. On the right-hand side is just kt. And very important here is the constant. Constants are extremely important for the ordinary differential equations because for a general, this C, for any constant, you have a general solution. When you use initial condition, you will find particular solution. So never forget this C when you are integrating ordinary differential equation. Okay, from here we have ln y, we have ln k minus y, and kt plus c. Okay, we have ln something minus ln something. If this is the case, this is the rule, right? This is if ln a minus ln b, ln a over b, or ln x and minus ln y. This is a fact. So this is why I made it in a different color. There's nothing to do with the flow of this solution. It is just reminding ourselves this was an equation that we can use for the logarithmic function. So I can write this part as a fraction, ln y over k minus y. So this will be, with this equation, this will be that. Again, kt plus c. And now I'm multiplying everywhere by minus. But if you multiply minus of ln a fraction, then that minus goes in and it will be a power. It's always the coefficients of the logarithmic power function. The coefficient goes up to the power. So if you put the minus 1 on the power here, it means that you're flipping the denominator and the denominator. So you have y over x. So if you multiply this by minus 1, so from here to here, you're basically flipping the inside, and from here to here, minus kt minus c. Why I'm doing this? Because the aim is to find out an equation is like a y is equal to something. Okay, when I do that, what we realize that if you take the exponential function on both sides, we will have k, but we have minus y over y, which is just minus 1. And we have exponential minus kt minus c. So exponential minus c is just a constant. I can use another name for that constant. Let's say a will be another constant representing exponential minus c. So that's a here, exponential minus kt. So this minus 1 will go up. There is a plus 1. Now, still y is in the denominator here. So how can I get the y is equal to something by just flipping the rational number, basically, numerator and the denominator. Swapping these two order, I will be able to get the y on the denominator, so I can find the y is equal to something. That's my aim. This is why I'm doing the flipping here. So y is in the denominator now, and k is a constant. I can take it on the other side. So y is equal to k over a e to the minus kt plus 1. This is a general solution. Another name for the general solution is implicit solution. So this is an implicit and or general solution. So this A is just any constant. So this A is, as you realize, coming from that C. Very important. Or we shouldn't forget that C, such that we will be able to have the general solution. Well, now we are going to use the initial values and we find some kind of A here and plugging in, and then that will give us the particular solution. This is the next step. So if we have the initial condition for us at t is equal to 0, y is equal to y0. Y0 represents here a constant, unknown constant. So let's plug this information into here. So we want t is equal to 0. If t is equal to 0, e to the 0 is just 1. So we have a, we have k, we have 1. And y is equal to y0. So this is y0. Y0 is a constant. And we can multiply this to here. A plus 1 y0 is equal to k. So we have a y0, that minus y0 will go to the other side. We have a, we want to find out a. So that's y0 will go to the other side of the equation. We will have a k over y0 minus 1. So this is the constant. And we need to put this constant inside to the general solution to find out the particular solution. Let's put a here. Well, that is the case now. Oh, we need to organize a little bit. And because we can multiply this one with y0, and then we can multiply this one y0. So that will be a one term here. And then this denominator will go up as a nominator. So we will have only one fractional part as a rational number. So this is the function, and y0 is the initial value. And that is the particular solution or explicit solutions for this model. Okay, now next part of this question says that state what happens to y at t goes to the infinity. So basically this means that you're going to look at the limit condition when t goes to the infinity. We know that exponential minus x when x goes to the infinity is 0. That means this limit will be 0. So everything here will be 0. So we only think we're left y0 k over y0. So it is just k. So the k is the, if the t goes extremely large, we will reach t, we will reach k. So k is the stable solution for this ordinary differential equation. Okay, what is the last part of this question? It's just we would like to find for what value of y is the rate of increase of y is maximum. So just before we start, reminding ourselves a fact. If we have a polynomial, a quadratic polynomial, something like ax squared plus bx plus c is equal to 0, if we take the first derivative, will be 2ax plus b, and then making this one is equal to 0 will give us the critical points, which will be just x is equal to minus b over a. If you look at the second derivative at that place, the second derivative of this polynomial will be just 2a. If second derivative is positive, then we have local minimum. So just recalling our knowledge here, I'm going to use this fact. So the rate of increase of y is dy over dt. It's a definition of a derivative. Left-hand side of the ordinary differential equation is a quadratic polynomial. I think the general solution. I'm looking at the general solution in that mode. Just I'm waiting for my computer to read those pages. Okay, so this is the general solution. Sorry, that yes, if dy dt is equal to, we are talking about the disk state. Sorry, we are talking about the disk state, dy over dt. So you have y squared something, y squared minus y. So this is a quadratic equation. That's the key. I just wanted to make sure I'm saying the right thing. See here. So this is left-hand side of the ordinary differential equations that I've just shown you, that give us this quadratic polynomial. And the critical points, as we've done here, when this is, take the derivative of this and make it equal to 0, that will be minus k over, yeah, that is x minus b over 2a. That is minus k over 2a. That's the a. So k will disappear. We will have only k over 2. So I'm just using this equation. So that's the critical point for this equation. And the coefficient of y squared is negative. Then k over 2 is the maximum point, is the local maximum. The second derivative of the test, if the second derivative is bigger than 0, is local minimum. If smaller than 0 is local maximum. If it is equal to 0, it does not give you any value. Just you know that second derivative of the test, just reminding yourself. In this case, this coefficient is negative. So the second derivative, it will be negative. So the point, the critical point that we obtained will be the local maximum point. So what is the value for y such that the y reaches to the maximum? Is that if y is equal to k over 2, we will reach to the local maximum. If for y is 0 is bigger than k, we always take the y0 between 0 and k in these questions when we are solving it. If y0 is bigger than k, what happens to y as t increases? So this is the question. If y0 bigger than k, then k minus y0 needs to be smaller than 0. If we take the limit when t goes to the infinity to the function y, well, this is equal to 0. This is whole everything is equal to 0, as we've done in one of the section above, that we have only k. But y approaches to k as t goes to the infinity. In general, what is happening is this. So you have y0 is bigger than k, is somewhere here, and y0 smaller than maybe somewhere here. So they are approaching. So this one is from the, this one is for approaching from above to the k. And the one of the section that we've done above, when the y0 is smaller than k, it approaches the k again, but from the below, right? But both approaches to k. So in the long run, the y values approaches to k. So y over k, this is just a general. This is nothing to do what we've done in the question. This is just a general knowledge. For a logistic curve, population model, given by these ordinary differential equations, Y over K is called the carrying capacity. Just in population model, you have anyway, I will just stick with the maths. I will not go through that one. Okay, that's all for this question. You really don't need this part. This is just an extra information. And the question finishes here. So thank you very much for listening. Hopefully it will be helpful for you. Thank you. Cheers.